Welcome everyone watching on YouTube. So this is our 119th live stream geometry. The IMO just happened recently, so we'll be covering one problem from it. And the rest of the problems I took from the All Russian Math Olympiad. So we may have done some of them in the past, but I don't think I remember the solution to most of them. So if you'd like to join me in the future, feel free to email me at mgreenbeta1@gmail.com. It's in the description of my video. And we meet every Sunday at 8 a.m. US Central Time. All right, so I will share my screen. Here is the first problem from the IMO. This is P2. So there was a really hard GEO problem, P6. This was the easier one from the contest. So I haven't solved it yet. So we have a triangle with AB less than AC. I think, the midpoint of arc CB. Okay, so containing A, will be point S. Let's draw perpendicular bisector. And that is S. Perpendicular from A to BC meets, okay, let's shrink this just a tiny bit. Drop a perpendicular, and it meets BS at D in the circle at E. Let's draw those 2 points. We have D, E, and we could call this F. And the line through D parallel to BC meets BE at L. This is L. And then we draw the circumcircle of BDL. And it meets the circle again at P. And then we want to show the tangent at P meets line BS on the internal angle bisector of BAC. Let me think about that. Something didn't go. So I didn't do something right here.
Oh, it's the tangent to the small circle of P.
Okay. And now that would make sense. So we want to see where it meets BS at this point. So we want to show AG as an angle bisector. All right. Wonder if these concur, or if that's just a kill. No. Okay. So let me think. If I'm drawing a tangent, I'm gonna just draw PG for now, but maybe eventually I want to extend it. I'm just gonna draw this to make it look nicer. All right. I don't know if it's worth trying the midpoint of arc BC, so I'll just do it. I mean, another way to phrase it is we want to show that AG and I are collinear. What K instead? Yeah, I haven't seen. What's interesting is the asymmetry of this problem. So We draw BS, but we don't draw CS. So SBC is isosceles, SBKC is a kite. I wonder what the other tangent is from G to this circle. Does the tangent intersect on AF? Looks like it might.
Yeah, it does.
All right. If I draw this point, I don't like I. I'll call it N.
And that's actually a really strong point.
Okay.
That lies on like PK as well.
All right. Interesting. So we have a couple things that we want to prove. So, I mean, basically we want to show dPBN is harmonic. So yeah, I guess we could first define it this way. And we want to show, yeah, how do we show dPBN is harmonic? Should we project, let's see. Maybe project through B onto the circle. But I don't know where N would go. It almost looks like N goes to the parallel from A to BC. That looks true.
Yeah.
L, P, and S are also collinear. Interesting. Yeah, a lot of good facts here, but we haven't proven. So, yeah, let's be careful.
LPS is very easy to show, and from that we also get, for example, P and K. And I don't remember how I proved B and I, but that's also doable.
Yeah.
Oh, that's also once we. Oh no, because LDN is 90 degrees, we get a lot of things. Like for example, we know that EBN is a 90-degree angle and EBI is also a 90-degree angle. And then we can see that the same way PNK and LPS are equivalent. And we can just prove either one of them, and LPS is just an angle chase.
Okay. So LP and S we can show is collinear by an angle chase, and then since we know this is a 90-degree angle, then that would prove that PN and K are collinear. Okay. And then B, N, and I. I wonder if L, N, and C, probably not. Okay, so this is an angle chase. This follows from the right angle. This one, I am not sure.
That one's also from the right angle.
Oh, really?
Yeah, because EBN is LBN is 90 degrees, and we also know EBI is 90 degrees.
Okay. So everything in this figure we know. And then from there, can we show that dPBN is harmonic? Seems like there's got to be a way once we know all that.
I can show that NG is a tangent, and then yeah, we'd be done with the harmonic bundle.
Okay.
So we need, wait, I wrote this down somewhere. If we use Pascal's theorem on EAS IB, sorry, EAK IBS, I think I labeled the points differently. We get that NG and the intersection of SE and KI are collinear, and SE and KI are parallel.
In fact, it almost looks like these concur. Okay. Maybe they do. So NG and the point at infinity are parallel.
Yeah.
Okay.
And then we can just angle chase now. GNP is also just IKP, and that's IBP, and that's NBP, and that's exactly what we need.
NBP. So sorry, did you show that did you solve the problem, or you showed that GN is tangent or something?
GN is a tangent.
Okay. So yeah, you're saying once you show that GN is parallel to, is it SE?
SE and KI. I'm using KI right now,
Okay.
but SE as well.
So yeah, once you show it's parallel, then an angle chase shows it's tangent. All right.
Yeah.
One sec, I'll be right back. Thanks for waiting. Try something. Oh, maybe G is the circumcenter of APN. That's what it looks like. And it looks like these also concur. So yeah, this is a pretty rich configuration. So can we show GA equals GN? ABNG is cyclic. Interesting. Oh, so that proves that GA equals GN because I'm guessing we can angle chase that this is an angle bisector. Yeah, we know it is because AS equals SI. And let's see, how do we know this is cyclic? Is that power of a point or just like an easy angle chase?
Because GN is parallel to SE, so ING is ISE, which is ABS. So ING is IES, and that is ABS.
Okay, interesting. So it's like Grimes theorem. All right. So then we know that G is the circumcenter of APN. I don't know that these three concur.
I think from that you can angle chase to prove that AGK is collinear.
AG and K are collinear. Once you know that these concur.
No, just AB and G is cyclic.
Oh, so you don't even need M really.
But how do you prove that NG is parallel to SE if you don't use that G lies on AK? Because I redefined G to prove that.
Oh yeah, sorry.
But I think we can just finish with the showing its harmonic idea.
Okay.
Because, well, if we define G again as the intersection of BS with AK, then we can project this cross ratio of BD and P. We can project through N at first onto AK.
Okay. So BDPN, project through N onto AK. So we get GKA and this point, right?
Yeah. And then now if we just project through G, we're done. Sorry, through B. Through B. Onto the circumcircle.
Okay. Then we get ASIK, which is obviously harmonic. Okay, so we're redefining G. Well, they don't define G in the problem, so we can just define it that way. Okay, so we define G that way, and then we prove that GP is tangent by showing it's harmonic. Okay. Was there anything that we assumed? Okay, so let's see what we actually needed. We need this collinearity, and then we need that to prove the other collinearity, right? I'm just trying to remember the order in which we did everything. So let's see. So let AK, might as well just say label the points as shown. Okay, so step one, you said, I think you said showing these are collinear as an angle chase, right?
Yeah.
Okay. Because let's see, we know this is a right angle. And then to show that this is a right angle, wait, is it trivial because this is 90 and this is 90?
Well, they're equivalent because these are both 90, but we need to show either LPS or PNK, and then the other one follows.
Okay. So
Um,
for LPS, we know angle LPN is LDN is 90, right? Does that oh, but we don't know PNK yet. I see. Okay.
yeah, we can do like LPB is LDB, and then we use the parallel. So that's just CBE. Oh, wait. Sorry, LDB. Yeah, that's CBS. So that's the angle over CS, and we want to show that it's the same as BPS, so the angle over BS, but they're just the same length.
Okay. Because CBS is BCS, which is BPS. So that, which is 180 minus BPS. Okay. So first we have angle LPB is LDB is CBS. So angle BCS, which is 180 minus angle BPS. I think that should be right. So that implies LP and S are collinear. And then that means that angle SPN is 180 minus LPN, which is 180 minus LDN, which is 90. So PN and K are collinear. So SPN is 180 minus angle LPN, which is 90. And that means that PD and K, sorry, PN and K are collinear. And once we know that, then we want to show SE is parallel to GN. Okay, so we define G to be the intersection of AK and BS. So first we showed that GN was tangent, right? Or did we define? I'm trying to think how we define things. So
G is the intersection of AK and BS, and we can show that GN is tangent.
okay, so N is the intersection of this circle with AE. Is that how we define it? I think so, right?
Sorry, wait, what? Sorry, can you repeat that?
So N is defined to be the intersection of this circle with AE, right?
Yeah.
Okay. And then we show GN is tangent. Okay. And that was an angle chase. Let me think about that. So you try to show that angle GNP is NBP, but NBP is PBI, I'm guessing, and GNP is IKP. Okay, so you had to show so showing that these are parallel is equivalent to showing the tangency, right?
Yeah.
Just Pascal.
Oh, Pascal, that's right. Okay, so by Pascal's theorem, Gn and Ik are, by Pascal's theorem, Gn is parallel to Ik. So I'm just trying to remember the point. So it's APE, let me think, APB, EKI, is that right? I think you need to ask.
Wait, AP, but we're not intersecting AP with anything. So we want GN in the intersection of SE and IK, so we can just go through an order like AKI B SE.
AKI BSE. Okay. AKI BSE. So AKI BSE. Okay. So I'm just gonna write that out for now. So by Pascal's theorem on AKI BSE, we have GNG and the point at infinity on KI or SE?
Well, the intersection of KI and SE.
Oh. That means NG is parallel to SE. So yeah, an easy angle chase shows that SE is parallel to KI. Yeah, I'll just say that. It's easy. It's easy to see.
Well, they're both diameters.
They're both, SK is a diameter, and EI is a diameter. So yeah, I'll say it that way. Yeah. So SK and EI are diameters. Parallel to KI. All right. Let me write this out. We have SEKI intersect SE. And then we have KA intersect SB is G. And then IB intersect EA is N. Okay. All right. And then so here's the angle chase. So I'm just gonna write it out. Angle GNP is angle IKP, which is angle IBP, which is angle NBP. Okay. So GNP is IKP is IBP, it's NBP, and that implies GN is tangent to omega. And then we project through, was it B? Or I know we project onto AK. So I forget what point we project through onto AK. N, or, oh, N. We project through N onto AK. So projecting through N onto AK, we get that BNBP. So yeah, we don't really need this circle, do we? Actually, do we need either? Well, okay, we'll get to it. So one step at a time. So projecting through N onto AK. We have BNBP. So I'm going to write it on paper first. BNBP and P is or what if I flip the order? So DB and P is equal to AM M G and K, which is equal to A I S K. Okay. Okay. And that implies GP is tangent to omega. Okay. And then from there, that basically means, so we know G lies on the perpendicular bisector of PN, and we know it lies on the perpendicular bisector of AN because this is cyclic and this is an angle bisector of this angle. So we would know G is a circumcenter of that. And then
but GP is tangent to omega is what we wanted to show, right?
Yeah, this solves it. We don't need any more.
Oh, okay, sorry.
Right. Or no, I guess I'm asking that as a question, but that's true, right? Like once we know this, it solves the problem, right? Okay. Yeah. Okay. Did we need point I? Oh yeah, we used it a couple times. We don't need J. So yeah, there's other interesting things going on, but we don't need them to solve the problem, I guess. So this solves it. This should be good enough. Yeah, this is very random. Like I wouldn't say this is like the most elegant problem, but it's interesting. Uses a lot of stuff. All right, so let's move on to this one. So we have a triangle where AC is greater than BC. I wonder if we want C to be at the top. That's what it looks like. So AC should be less than BC. So maybe like this. And we have a circle passing through A and B. And it meets the segments at A1 and B1. This is A1. This is B1. And then we have the circumcircle of A, B1, C, and ABC. And they meet at P, different from C. So that's P. Then A, B1, and A1B intersect at S. I don't know why. For some reason, this makes me think of Desargues' involution theorem, but Q and R are the reflections of S in each of the sides. So it should be Q, and this should be R. And we want to show PQRC is cyclic. All right. Okay. So let's see how we can show that these are reflections. So we could draw CS, and then we have two kites. So basically, C is a circumcenter of QRS, right? I think that's true. Yes. You don't want it to look like A1 lies on it. But yeah, C is the circumcenter of QRS. So that means if PQRS is actually cyclic, I wonder if we have some kind of angle bisector. Like, it would mean something. So just a sec. Let's see. So we'll label these points. So let's see if that circle passes through any other point. Not that I see right now. unless maybe this point, but I don't even know if those circles always intersect, so. Yeah, I'm just gonna delete it for now. All right, let's see. Yeah, this is a very general configuration. Yeah, you can move A1 wherever you want. I wonder if there's a way to make it so that P, like for example, if I make this like if I made this like an obtuse triangle, then P, basically we'd want to show, so we'd have CR equals CQ, and we'd want to show that cyclic. Yeah, I was trying to show something with like angle bisectors, but I don't know if it'll work. Basically, we want C and P to be on opposite sides of QR, and then we could show that. I don't know if that's possible.
I think I have a idea that gets us at least pretty close to a solution.
Okay.
We can use, we want to use the power ratio lemma to show that the ratio of powers from Q and from R, respectively, to these circles like ABC and A1B1C is the same. And we know that I think we can find a way to, since Q is the reflection of S over line AC, we can probably find a way to relate that just to the distance from the circumcenter of A1B1C to AC.
Okay.
If we draw both of these circumcenters, we'll see that the circumcenter of A1B1C is on the altitude of ABC. So actually CF and CG, or yeah, maybe CF and CO are just isogonal. So a lot of the stuff should just cancel out. I haven't done the calculation, but I think it will just work out.
Okay. So yeah, the power ratio lemma, that's a really good idea. So we want the powers of Q with respect to these two circles. So the difference between, so we can use Casey's theorem. So we know this circle. So the difference between the power of Q with respect to this circle, which is 0, and this circle, it would be 2CF. But that would be times the distance from Q to PC. And then for this circle, it would be 2CO. Oh wait, never mind. But you want to find a way to get the power of Q with respect to this circle, you're saying?
Yeah. And I think we can do that just in terms of the power of S to that circle and the distance from of F to that line we're reflecting over.
Okay.
That, well, I'm writing it down right now. I'm not sure if it'll work out, but it looks promising.
Okay. All right, let's see. So yeah, if we know the power of S with respect to this circle and we know Q is the reflection, I'm thinking how we would use that. But yeah, the power ratio lemma, yeah, seems like a good idea. So angle CRQ is 180 minus CPQ. And CQR is CPR. So another way to say it is we want to show CPR is 180 minus CPQ. Okay, so that would mean that CP bisects this angle, basically. So yeah, we want to show CP is the external bisector of PQR. That would solve the problem. So I'll just delete that for now. Yeah, I'm going to draw this. Maybe we could let PR and PQ meet this circle. And we want to show PC is the bisector. PS bisects QPR. Huh, I didn't know that. So if that's true, then it would be equivalent to showing this is a 90-degree angle, right? Is that true? Interesting. That's pretty significant. Hi, Coffee. Thanks for joining us. But yeah, is it obvious that this is a right angle?
Yes, because P is the Miquel point of AA1, B1.
Oh, okay. So yeah, if we wanted, we could draw this point of concurrency, right? Let's see. And yeah, that's like a well-known fact. Interesting. This circle almost looks tangent to AB. There we go. So have you made any progress on the trying to use the power ratio lemma?
No, not really. It's not as easy as I thought.
Okay. So yeah, you take S, you reflect it over the two sides, and then you want to show PS bisects QPR. So yeah, that seems like a fairly simple statement. But yeah, let's see if we can prove it. I mean, maybe the law of sines, like we have sine QPS over QS is sine PQS over PS, and the same thing on the other side. So I wonder, so if this were cyclic, then this, if it was an angle bisector, would meet it at the midpoint of like the arc of that circle. So I wonder if there's something special about that point. It's a little hard to draw here, but I just shrink the diagram a little bit. So let's see. So PS, it would meet the circle at circumcircle PQR. So it would meet this big circle at this point. And then CH would be like a diameter of that circle. Maybe it's isogonal with CS.
I think that like triangle PQS is similar to PA1B1.
PQS is similar to PA1B1.
Yeah, but I can't find a proof to it.
Interesting. Okay. So I'm gonna undo all that because I think
The similarity is equivalent to, for example, QA1 and SB1 intersecting on this on the circumcircle of A1B1C.
okay. QA1 and SB1.
Yeah.
So we have QA1 and RB1. Interesting. So why would that be? Once we know the similarity, do you know if we can then solve it with an angle chase?
Yeah, but I don't use power ratio lemma like Johannes.
Okay.
Yeah, that doesn't seem to work as well, so maybe that's a good thing you're not using it.
So yeah, we can like hide a lot of the problem if we just want to show that Q, A1, and K are collinear. Yeah, we don't even need point P, right? We just draw the circle of A, B1, C1 that meets us at K. And then we just reflect S over. Oh, so I think that's obvious actually. Well, because angle SA1E is angle QA1E, and angle KA1E is KA1C, which is KB1C, which is AB1C. So we just have to show AB1C. Let me think about this. Okay, so we just need to show that this angle, that can't be true. Is it true that CA1S is CB1S? I would be very surprised. I don't think I did something right, but oh, it is true. Wait, why is that?
Because AA1B1B is cyclic.
Cyclic. Okay, so I think that solves it. So yeah, we can, if we let K be the intersection of these, we can show that QA1 and K are collinear by an angle chase that's not that hard, because basically we just want to show QA1C plus KA1C is 180, but QA1C is just SA1C. And KA1C is just 180 minus KB1C, and then it's easy. So, okay, so yeah, we can show that those concur on the circle. And then you said by an angle chase, that shows the similarity of two triangles that Pascal mentioned.
Yeah, now it's just this lemma that like P is the center of the spiral similarity that takes I don't remember the two triangles we were trying to show.
All right. So
That takes like QS to A1B1, I think. Yeah. And we have
so PQS
we have
to PA1B1.
yeah, we have the circle A1B1 PK already. Wait, I'm a bit confused now. Oh, we might still need to show PQKS. I'm not sure. I thought it was equivalent, but I'm not sure anymore.
Okay.
Yeah, I think that wasn't enough.
Okay. So if oh no, that is enough, because if PQS is similar to PA1B1, and then PRS would also be similar to it, then this has to be an angle bisector, because they're just angle QPS is A1PB, and angle RPS would, by the same logic, be a P1B, right?
Yeah, I was just saying that like this concurrency, that K, A1, and Q are collinear, that's just a consequence of the similarity. I said before that it was equivalent, but that was wrong.
Oh, okay. So you saw it in one direction, but you're not as sure about the other direction.
Yeah, I think we just need like, for example, PQKS would like that being cyclic would be enough.
Would solve it. Okay. And that seems like it's probably an angle chase, because we want to show this plus this is 180. But this angle is 180 minus A1CB1. So maybe it's not as easy as I'm thinking. Yeah, PQKS. If we can show that cyclic, that solves it. I think we know QRKJ is cyclic. I don't know if it helps. No, I don't think that's true. But yeah, confused. One sec, I'll be right back. All right, thanks for waiting. Sorry about that.
I think I can show that PQKS is cyclic.
Okay.
So first, you know that CPS is 90, so that's well known.
Mhm.
So you get that CPES is cyclic.
Oh, interesting. CPEDS, or yes.
Yeah, so we have that PKQ is PKA1,
Okay.
and that is PCA1, and that is PSE, and that is PSQ.
Okay. PKA1, and that PSE is PSQ. So PKA1
It's PCA1.
is PCA1. Okay. Just PCE. Okay. So sorry, I'm just trying to keep it all in my head. So PKQ. So we're trying to show PSQ is PKQ, but PSQ is PSE, which is PCE, which is PCA1, which is PKA1. Okay. All right. So I'm going to write this down and then type it up. So angle PSQ is PSE, which is PCE, which is PCA1, which is PKA1, which is PKQ. Okay. So I think that should solve it. So I'm going to get rid of point G here. Then I will type it up. So let this circle, so CPA1B1, meet AB1 and AC1 at K and J. Yeah, I could just say like label the points as shown. But I guess then it's not obvious that we had to show that those are collinear. So maybe I won't write that. So let CA1B1 meet AB1 and BA1 at K and J. So then we do an angle chase, so to show that these are collinear. So okay, so this angle is this angle, which is 180 minus this angle, which is 180 minus this angle. So so QA1C, I'm just going to write it on paper and type it up. Minus A1B minus AB1B, which is AB1A, which is A, which is AB1C. which is 180 minus, which is KB1C, which is 180 minus KA1C. So that's kind of a long angle chase, but I'll type it up all right now. I could probably, I'll just type it all out. So angle QA1C is angle CA1S, which is B, which is 180 minus angle AA1B, which is 180 minus angle AB1B, which is angle AB1C, angle KB1C, which is 180 minus angle KA1C. I think that's the full thing. So let's check that. So we have QA1C is CA1S, which is CA1B, which is 180 minus AA1B, which is 180 minus AB1B, which is AB1C, which is KB1C, which is 180 minus KA1C. So that shows that QA1 and K are collinear. And then similarly, R, B1, and J are collinear. Right. And then we want to show, okay, so P is the Miquel point of A1, of the cyclic AA1B1B. And that implies that PS is perpendicular to PC. Then next we show that so that implies that PES DC is cyclic. And then we could do the angle chase. So I'm gonna type it out. So angle PSQ, PSE, PCE, PCA1, this angle PKA1, PKQ. And so that implies PSKQ is cyclic. And then similarly, RJS or RS, RPSJ is cyclic. And then once we have that, then we can show that PQS is similar to CA1B1. Oh, that's a very easy angle chase after that. Because angle PQS is PKS, which is PKB1. And we want to actually. Oh, PAB1, sorry. So PKB1, which is PAB1. So I'll just say by an easy angle chase, we would have PQS similar to PA1B1, which is similar to PJR, or let's see, PQS, PRS, or PSR. And so that implies that PS bisects angle QPR.
That's triangle PJR, not PSR.
Oh, PJR. Thanks. Bisects angle QPR. And that means that PC is the external bisector of PQR. So and then once we have that, since CQ equals CR, it follows that that's cyclic. Okay. So let me just make some space. But yeah, the Miquel point is the key fact here. All right. So CQ equals CR. PQRC is cyclic. Right. So I'll move on to the next one. So yeah, because C would be the intersection of the external angle bisector with the perpendicular bisector. All right, so here is the third problem. We have a triangle ABC. L is the foot of the internal bisector of angle B. Yeah, it's weird. They put, like, one problem had C at the top. This one has B at the top. Let's draw the angle bisector. And the foot of it is L. D and E are the midpoints of arcs A, B, and BC. So yeah, maybe it's worth drawing the intersection of this with a circle. So yeah, I actually had a tool for this that would have made it easy, but that's weird. It didn't draw the midpoint of the arc. Okay. Oh, it did. It just called it something different. Okay, so but yeah, everything is named weird. A, B, and BC. So we want that to be D and E. Should be D and E. And of course, we have a bunch of kites. BDIE is a kite using the in-center, X-center lemma. Let's call this K. And yeah, we have a bunch of kites. P and Q are on the extension of BD and BE. So that APB equals CQB. Okay, so we drop perpendiculars to those. And we want to show the midpoint of BL lies on PQ. So this is, oops, that's P. And let me drop this one. So P and Q. Russia has good problems, I feel like. Q. So we want to show the midpoint of BL. In other words, PQ bisects PL. I wonder if they're perpendicular too. Don't think so, but let's check. Oops. Yeah, they're not. Okay. All right. So yeah, BDIE is a kite. Yeah, so we have the in-center, X-center lemma, of course. We can use it a bunch of times. If J were the midpoint, so the midpoint of AB would be the center of, maybe it's worth drawing these circles. If this and this, this is the altitude, and the centers of these circles are collinear with J. I don't know if that makes it easier or harder, but it does something. So it's N, and we call it O. Let's call it something different. So those are collinear.
Maybe P is not ideal because we already had P.
Oh, okay. So let's call it X. So let's you know that NJ and X are collinear, and we want, yeah, we could try to show that NJP and XJQ are similar. So NP and XQ are radii. So actually, so we know the ratio, right? Because we know NP over XQ is NB over XB, which is NJ over JX. So we just have to show the angles are equal. Okay. And that doesn't look like it should be that hard. Yeah, that looks like it's probably just an angle chase, yeah. I think that solves it. I'm just going to write out the angle chase, but yeah, this looked kind of easy. Okay, so angle PNJ is PNA plus angle ANJ, which is PNA is twice angle PBA plus 180 minus angle A. And PBA is DBA. In fact, I'll just skip that step. So angle DBA is C over 2. So that would just be angle C plus 180 minus angle A. And we'd have angle B, angle A. Yeah, it's not a hard angle chase really. Okay, which is angle NXB plus so yeah, can we show angle CXQ as angle A? Shouldn't be that hard. Because
Well, it's the same thing as on the other side, right?
Oh,
Like
yeah.
it's 2 CBQ, and CBQ is CBE is CAE, so that's just 2 times alpha over 2.
Yeah. Okay, so plus 180 minus, so angle A is angle BA is twice angle BAE, which is twice okay. Okay, so I'm just going to type this up. But yeah, I mean this is a pretty easy problem. So let J be the midpoint of BL. I'll say let N, J, and X be the midpoints of BA, BL, and BC. Okay. We have NP over XQ. NA over XA, which is NJ over XJ. So that's the first step. And then by an angle chase, PNJ is JXQ. And that implies that PJ and Q are collinear. Which solves the problem. All right. So yeah, the angle chase is not hard. I'll write out half of it. So we have we can do a similar calculation with NXB. We'll say JXQ. Right. All right. So I'll move on to the next one. Let's see. Let me see if I can find a hard. This one looks a little tricky. So we have three medians. And we want to show that we have coaxial circles. Probably not as hard as P6 of the IMO, but still, let's see if it's hard.